Okay, this is just a bonus video following up on the last one about hypothesis testing. I'm going to go through a couple examples real quick, but it involves using some concepts from statistics that we haven't really discussed in detail yet. So if this is beyond your training level at this point, or it's been a while since you've had statistics, no worries, as long as you can kind of just understand the concepts from the last video. But if you were wondering how a statistics program spits out a p-value or determines whether you should reject the null hypothesis, this video is going to give you a little peek into that. So I'm going to start by finishing our Memorex example from the last video, kind of really quickly here, using some actual numbers. So as a reminder, we were testing whether a new drug, Memorex, would increase people's memory scores, so we're laying out our two competing hypotheses. The null hypothesis, age 0, that our population mean of Memorex users is no better than the general population, meaning they're less than or equal to the general population's mean, which we're going to give with this Greek letter mu before, just like before. Then we contrast that with the alternative hypothesis, H1, that the population mean, mu, for people taking Memorex is indeed higher. It's greater than mu of the general population. So that's what we're testing here. And indeed, in the last video, I gave some basic fake data in the example. I said we know the general population's memory scores are normally distributed, that's the big N up top here, with a mean of 50 and a standard deviation of 10. And I mentioned that our sample of 36 Memorex users had a mean of 55 for their memory score, which is indeed higher than the known general population mean, but that's just for these 36 people. The question is it extreme enough for us to conclude Memorex users overall would be higher than the general population? So probability theory is going to let us create a distribution of sample means for all the possible size 36 samples that we could take if the null hypothesis was true. So if we kind of took them randomly from the general population, the population that has a mean of 50. In other words, if the null hypothesis is true and Memorex is no better than general memory, we can look at what all the possible size 36 samples would look like from a distribution centered at 50. Now technically the distribution we're creating, so I'll show you a little normal curve-shaped graph up here. This distribution of all possible sample means it has a standard deviation that's not exactly the 10 of our general population. Actually, it's going to have a standard deviation of that 10 divided by the square root of the sample size. So 10 divided by 6, because that's the square root of 36, square root of our sample size, which is 1.6667. So probability theory proves that the distribution of all possible sample means, if the null is true, will have this mean of 50 and this standard deviation of 10 over the square root of the sample size. So it comes out to 1.6667 as its standard deviation. And now we've got our graph of possible sample means to see where our actual sample mean of 55 lands, to see how kind of unlikely or likely our sample mean is out of all the possible sample means you would be likely to see when the null hypothesis is true. So now we're asking, what proportion of size 36 samples from the general population, when the null hypothesis is true, would come out as 55 or more? Where does our M of 55 fall on that little graph in the top right? And in this case, 55 is how far above the mean? How far above 50? Well, it's 5. It's 5 above the mean. It's 5 above 50, right? So what is that? That is 3 steps of this amount. 3 steps of 1.6667. It's 3 of this graph's standard deviation, right? So just meaning our sample was kind of 3 steps of this distribution's standard deviation, which we call a z-score of 3. That's just the terminology for steps of standard deviations. So again, it just means our sample was 3 steps of 1.6667 above the center of this graph, which was at 50. And we're saying 3 steps of 1.6667, that gets us 5 above 50. It gets us to 55. That was our sample, right? Just means our sample was 3 steps above, z-score of 3. Now, at this point, if you're not using a stats program, you have to consult what's called a z-table or a standard normal table, just for a standard normal curve, a curve like this. And that would tell us that only 0.0013 or 0.13% basically 1/10% of size 36 samples randomly taken from the general null hypothesis population would have a mean memory score of M55 or higher. So this number here, this 0.0013, that's the p-value for our sample. It's the probability of getting a sample mean at least as extreme as 55 when the null hypothesis is true, which is quite unlikely, really, right? That's a low percentage, low chance, which means it's very unlikely that our m equals 55 sample was just a random size 36 sample from what we would see if the null was true. Thus, it seems intuitively more likely that Memorex works, that the Memorex population is higher than the general population. So we reject the null hypothesis and accept H1. We go out and tell people we have evidence that Memorex works. Although, of course, in reality, we would want to repeat the study many times, maybe even have some independent laboratories replicate the study, and hopefully use even larger sample sizes long before we run off and convince people to take a new pill. But let's move on and do another kind of silly little example. So let's practice this idea first of setting up null and alternative hypotheses. So imagine a super fan of the show Game of Thrones has categorized the height of every character in the show and determined that the average character is, let's say, 66 inches tall. So mu for the entire cast, the whole population mean for the entire cast, is 66 inches. Then you watch an episode focusing heavily on the Lannister family, and maybe you hypothesize that the Lannisters are shorter than the average cast member. So try writing out H0 and H1 for that. Like, pause and give it a shot before moving on. Well, there's a couple ways you could write it. You might have written it out like I did on the left here. The alternative hypothesis being that the Lannister population mean is below 66 inches, and then the null hypothesis would be its opposite, the greater than or equal to sign. And remember, the null hypothesis is always the one with an equals sign somewhere in it. Or alternatively, you might have written it out like I did on the right side here. So H1 is that mu of Lannister is less than mu of the entire cast, and H0 is just the other possibility that Lannisters are greater than or equal to, that they're not shorter, they're not less than. So that is how you'd set up the null and alternative hypothesis. But again, we might want to actually carry out a statistical test and see if we have evidence of that from a sample that we take. Now, a statistics program can crunch those numbers for you quickly and easily once you got your sample, but to get an idea what such a program is doing, let's do it by hand real quick. So let's say we know the heights of the entire cast are normally distributed with a mean of 66 inches. We talked about that before. And let's say a standard deviation of 8 inches, just in that general population of the whole cast. So I put that in the top left here just so we remember it. I've also copied our hypotheses up there in the top left. And then what we're going to do is we're going to take a sample of size 4 by getting the height measurements of just 4 Lannisters. And we're going to average those 4 heights to get a sample mean. So a mean, an average across our sample of 4 people, might be a mean M of 56 inches. Now our question is, just given this data, our question would be kind of what proportion of size 4 samples, if we randomly selected from the entire cast, would be less than or equal to 56 inches? Like, imagine the null hypothesis is true. Imagine Lannisters are not shorter on average. If so, what proportion of the time would measuring 4 of them give us a sample mean of 56 inches? So we set up the distribution of all possible sample means for samples of size 4. Again, what the graph would look like if the null hypothesis was true. It would be a normal curve, like in the corner there, and the normal curve of samples taken from the population of the whole cast would have a mean of 66 and a standard deviation of not 8, but for this whole distribution of all possible samples, it's 8 divided by square root of the sample size. So the square root of 4, our sample size is 4, square root of 4 is 2, so we're going to divide 8 by 2, and that gives us 4, which means our little graph here is centered at 66 and has a standard deviation of 4. That number 4, we often call that the standard error of the mean. or SEM. That's what this little symbol here is for. But the standard error of the mean, the SEM, it's just on average how much a size 4 sample will be away from the center 66. If you take a size 4 sample, on average, how far would it be from 66? So then we ask, how many steps of that? How many steps of the standard error of the mean? How many steps of 4 is our sample below the distribution's mean of 66? So we had 56 as our sample, which is 10 below 66, right? We were 10 below 66. How many steps is that? Right? Being 10 below means 2.5 steps of 4. 2.5 steps of our SEM, right? So our sample is 2.5 below. That's a negative 2.5 for the z-score. It's 2.5 z-scores below the middle of the distribution graph. Then we just need to know how rare that is. Like, what kind of z-score cuts off 5% of the graph? And are we more far out than that or less far out than that? And again, we would need to consult a z-table for that, a standard normal table. And if so, we would find out that being 2.5 SEMs below the mean, so having a z-score of negative 2.5, it only happens in 0.0062. So in 0.62% of size 4 samples that were randomly taken from the whole cast, like if the null hypothesis was true. Only in that tiny proportion, 0.0062, would we have a mean height of 56 inches or less, which means it is incredibly unlikely, if the null hypothesis is true. We would almost never sample 4 people from the population, the entire cast, and have them average 56 inches or less. So we're going to reject the null hypothesis, which means we can accept the alternative and conclude that, likely, Lannisters are shorter than the rest of the cast. All right, hopefully that wasn't too complicated, but let's try one final example. In this case, let's imagine you're the head of quality control for a food company. You're maybe interested in monitoring the weight of, cherry tomatoes that are coming off the factory line. Because packages that are too light, if the machine is broken and packages are coming out lighter than they're supposed to be, that can lead to customer complaints. You didn't give as much as you promised. But packages which are too heavy, that's going to increase your shipping costs and decrease your profits. So that would also be bad. So what we've got here, let's say each package is labeled 227 grams. That's the promise. That's how much we want in those packages on average. And let's say the packages made by this packing machine, we know they're supposed to average 227, and we know the standard deviation of that whole population of packages is 3 grams. So it's the mean and the standard deviation of what things are supposed to be when the machine is working. Now you want to know if the machine that's weighing out the packages is doing its job correctly or if it needs to be recalibrated. So in other words, you want to know if it's churning out packages that are too heavy or that are too light. So what might your hypotheses look like? Pause and try writing them down before unpausing. Well, here's one way we might write it out. The null hypothesis would be that packages coming out are averaging 227. They are what we want. They're no different than the 227 goal. That's great. That's the null hypothesis, that everything is working fine. Then the alternative hypothesis, H1, is that mu is not 227 grams. In other words, that the machine is churning out packages that, on average, are not 227. So it needs some recalibration. Now, in that case, either too heavy or too light would be an issue. So your alternative hypothesis here would be a not equals sign. And thus, the null hypothesis must be an equals sign, since the pair of them have to match up, right? And of course, the null is always the one that includes an equal sign in it. All right, so we've got our hypotheses, but then to actually test it, we need to take a sample of packages coming off the line. How big of a sample? Well, let's just say we choose to weigh out 36 packages. That'll be our sample, size 36 sample. So we take a sample of 36 packages, n equals 36, and we weigh them. And our sample mean m in that sample might be, let's say, 225.5 grams. So is that evidence that we should shut down the machine and recalibrate things? I don't know. We need to run a statistical test to find out. And again, we could have a stats program do this for us, but just to get an idea what the stats program would be doing, we're going to check it by hand. We're going to do it by hand this time. So first, we could choose our alpha level, and we'll just use the usual standard 0.05, the sort of 5% alpha level cutoff. Then we might set up our distribution of sample means, which, as always, it's the distribution of what we would expect samples of size 36 to look like if the null hypothesis was true. In other words, this is the distribution of what all possible size 36 samples will look like when the machine is running properly. We're going to say the most extreme 0.005, right, because that was our alpha level, the most extreme 0.005, the most extreme 5%, those are samples that we would call unlikely to happen when the null is true, unlikely to happen when the machine is running right. Then we can use a z-table, so a standard normal table, to see what z-score cutoffs would put 5% into those two tails. So if you do that, you might find that it's, so we need to figure out what those are. You look at the table, it might tell us a z-score of 1.96 on the right side or negative 1.96 on the left side. Maybe that's what cuts off 5% into the tails. So basically it gives you 2.5% of the graph on each side, right? So that is the critical region, or what we might call the rejection region. If our sample of 36 packages has a mean that falls all the way out there, then we would conclude the machine is messing up. We would reject the null hypothesis H0. Which means we just need to know the z-score of our sample. The z-score for our sample mean, which had, again, 225.5 grams in just the 36 packages that we measured. So what is our sample's z-score? How many steps above or below the mean is it? Well, z-score, it's just, steps of the SEM, the standard error of the mean. So kind of the steps of this graph's standard deviation. And we want to know how many steps away from the center of 227 our sample was. So we know the distribution of sample means here. Our graph here has a mean of 227, right? It has a mean of 227 because the null hypothesis is that it's working fine with an average of 227. And then we can calculate the spread of this graph if we know the sample size we're using, right? It is the standard deviation of our normal packages, which we said at the start was 3 grams, but divided by the square root of the sample size. So 3 divided by the square root of our sample size, that's 3 divided by 6. So our distribution of sample means has a spread of 0.5 or half a gram. So a z-score is just asking, it's just how many steps of half a gram our sample is away from the 227, the null hypothesized middle. So looking at our sample, how many steps of 0.5, how many steps of half a gram are we away from the middle? Our sample, 225.5. It is, let's see, that's 1.5 below the graph's mean. So it's below the null by 3 steps of half a gram, 3 steps of 0.5. That's 3 standard error of the means, 3 SEMs. So the z-score of our sample is -3. Okay, so we're 3 steps below with our sample here. So the question is, z-score of -3, is that further out than the cutoff region, right? That's kind of just what we're asking. And yes, our z-score of -3 is way out in the tiny, tiny, tiny tail on the left here. It is out past the cutoff, the cutoff z-score of -1.96. So our sample is definitely out here in the rejection region. We reject the null hypothesis. We conclude the machine is not working fine and it needs recalibrating. So basically, we started by assuming the null hypothesis is true and the machine is working fine with an average of 227. When that is the case, how often would we see a sample of 36 packages where the sample mean has 225.5 grams? Not very often. It is very unlikely. It happens less than 5% of the time, much less than 5% of the time, right? This tiny little bit down here. So another way to summarize this one, we used our chosen alpha level, the standard 0.05, and since we had a non-directional two-tailed hypothesis as our setup, we need to put half that alpha level in each tail of the graph. So we can look up in a table, look up in a z-table and see that that happens at a z-score of 1.96 on the right and negative 1.96 on the left. Okay, so that's the z-score. Then we want to see how unlikely our sample mean is. How many z-score steps below 227 are we for our sample? And our sample of size 36, it had a mean of 225.5, which again was a z-score of negative 3. So you can look it up on the table, and that z-score of negative 3, I mean, clearly it's going to be further out. So we already can tell that it's going to be in the rejection region, right? It's more negative. So the z-score out here, it's clearly going to be in the rejection region. But specifically, you could look it up in the z-table, and you could even find the exact amount in the tail that's going to be past our sample's z-score. So it's 0.0013. That's the proportion in the tail to the left of that, like way out past it. Just 0.13% of the whole distribution is out that far or further. Which means our sample, yeah, it's clearly out in the rejection region, past the alpha level cutoffs that we drew above. Those ones put 2.5% in each tail, and we're even further out there, where there's less than 1% in the tail beyond our sample mean's z-score. So that's why we're rejecting the null and concluding the machine is busted. Specifically, we would say the p-value, the p-score of our sample here, the p-value is 0.0013. Like less than 1% of the, or less than 0.13% of the time, we would see a sample mean this extreme. Sample of size 36 with a mean this extreme, if things were working well, if the null was true. Now, by the way, if we had started with the suspicion that the machine is popping out small packages in particular, like if we had had a directional one-tailed hypothesis that packages are coming out less than 227, then we're still going to deal with the same p-value of 0.0013. The probability of a sample mean being that far in the left tail is still 0.0013, a very small p-value. You only get samples that extreme or more extreme 0.13% of the time if the null hypothesis is true. But the steps, if we had a one-tailed hypothesis, the steps would have been the same basic stuff we did before. But now for this one-tailed directional test, right, you write the hypotheses a little different, but we're still going to use alpha level. We'll choose our alpha level first, report what that is. Usually it's 0.05. Then we put that amount in the tail or tails, but since now we're doing a one-tailed, right, a directional one-tailed hypothesis, we would put all 5% in the tail over there. And we'd have to look up in a table, what is the z-score that cuts off 5% in the left tail? Which, if we look it up in a table, it is a z-score of negative 1.64. So that gives us the rejection region. Then we just need to know if our sample's z-score is that far out or further. And since our sample of size 36 had a mean of 225.5, and that came out to a z-score of negative 3 for our sample, meaning the spot where only 0.0013 proportion of the graph is out there, then we know our sample is further out than the cutoff that put 5% in the tail there. So in other words, if the critical region beyond the negative 1.64 z-score, we're out in that critical region for sure, right? With our negative 3 z-score. We are out in the rejection region, so we reject the null hypothesis. So whether it's a two-tailed hypothesis or like this, a one-tailed hypothesis, the steps are basically the same. There we go. Okay. So what you do, the steps, basically you could think of it as just write down your null hypothesis and your alternative hypothesis. That's going to tell you whether you're doing a one-tailed or a two-tailed test. Then you choose your alpha level, which is almost always going to be 0.05, at which point you can draw out that curve, that distribution of sample means, distribution of all possible samples of that size. Then you split your alpha value, right, the 0.05, the 5% or whatever, split that into one tail or two tails, depending on your hypotheses. And again, to do that, you can use a z-table to figure out what the z-score is that cuts off that proportion into the tail or tails. That sets up your critical region or your critical regions, right? And then at this point, you look at your sample mean. So you've collected your sample, got its mean, look at your sample mean, and you want to compute its z-score in that distribution of sample means. In other words, how many steps, how many z-score steps is your sample mean away from the middle of that distribution we laid out, that graph we made? And to calculate that z-score of your sample, remember to use what we call the standard error of the mean, the SEM, which is where you divide the original null population's standard deviation, divide it by the square root of the sample size. That gives you the SEM, the standard error of the mean, and you count how many of those, how many SEMs away from the middle of the distribution your sample was. That is your sample's z-score. And if you're further away than the cutoffs you made in step 2, if you're further out into a tail, into a rejection region, then you reject the null hypothesis. Now, if your sample mean isn't that far out into a rejection region, then you fail to reject the null hypothesis. Remember, that's the kind of thing we can conclude here. If the z-score for our sample is out in a critical region, then we reject the null, which does indeed let us accept the alternative hypothesis. At that point, we might say the effect is statistically significant. In other words, there's evidence from our sample that the whole population has a real effect, a real difference from what the null hypothesis claims. You would conclude there is very likely an effect, even if we haven't proven it 100%. But if the z-score in our sample is not in the critical region, if it's not in the rejection region, then always be careful to say that you fail to reject the null. Do not say that you accept the null. We never accept the null hypothesis. What we would say is we did not detect a statistically significant effect, or we failed to find a statistically significant effect, which people often shorten to just saying the results are not significant. But not significant doesn't mean the null is true. It doesn't mean we accept the null hypothesis. It just means we didn't have enough evidence to reject it. So at this point, maybe it's true, maybe it's not. The question is still open. All right, we're going to stop there for now. If you haven't studied a bit of introductory statistics or it's been a while, this video might have been a bit too much in detail, but hopefully you're starting to at least vaguely see how we're deciding whether our sample mean is unlikely enough under the null hypothesis that we would want to reject the null hypothesis.